Hello, I'm John Linford. Thanks for coming to my talk here at Bliss Retreat. I'm going to show some performance projections on future ARM CPUs, specifically the Neoverse V1 CPU, and look at the performance of Bliss kernels on that platform, and then as a reference point, show some of the performance from the Fujitsu A64FX. So the question I'm trying to answer is, will SVE code developed on A64FX port forward to the Neoverse V1? The Neoverse V1 at the moment doesn't exist, whereas the A64FX does, so this is a cross-generational comparison. And the A64FX was designed for specifically for leadership class HPC, while the Neoverse V1 can be used in a broad range of applications depending on how the ARM partner licenses it. So I'm not proposing a comparison of A64FX and Neoverse V1. I'm simply providing two data points from CPUs that both implement ARM's Scalable Vector Extension, or SVE. I'm going to show our simulation process for these future cores, things like the V1 and others, and talk a little bit about the tools we use to try to understand the performance of applications on future cores from ARM. I'll show how you can build Bliss for use in a simulation, which turns out to be really easy and quite nice. And I'll present the experimental results, going into detail on the performance and efficiency numbers for BLAS L2 and L3 kernels from Bliss. So a quick word about ARM's CPU IP roadmap. ARM is, because we are fundamentally an intellectual property company, we're providing CPU designs to partners who then go and implement them. And the designs we provide fall into three basic classes, at least for the CPU cores intended for infrastructure. These are the V series, the N series, and the E series. Many of you are already familiar with the N series cores because this is the same CPU core that appears in the AWS Graviton 2 and the Ampere Ultra. And it's proven itself as a pretty viable platform for commodity HPC workloads. Especially computational fluid dynamics performs very nicely here. But this platform has only two 128-bit Neon units, so its overall floating point performance is fairly limited. The V1 is the first V-series core from ARM, and this is a core designed with performance first. So it's intended to have a 50% single-threaded performance uplift over the N1 core, and to get there, ARM implemented SVE in a 2x256-bit configuration, and also added support for things like bfloat16, which is pretty nice. So I'll be taking a close look at the Neoverse V1, architecturally and performance-wise in simulation, and then talk a little bit about how SVE code written for today's architecture, specifically the A64FX, performs on this future architecture, which implements SVE, but in a lower physical bit width. So the V1 has half the total vector throughput, total vector capacity of the A64FX. How will that affect SVE code? Typically, when ARM designs a CPU, we try to balance performance, area, cost, a great many factors. And so the ARM CPU designs tend to be very balanced. And this is in part why they're so successful. But it means that when it comes to raw performance, and especially in theaters where the performance of the chip is ultimately the deciding factor, such as in HPC applications, ARM has a little bit more to do. So to answer this challenge, ARM has created the V series of CPUs, where the design philosophy is performance first. When there's a trade-off to be made between cost or power or area or something like this, we try to favor performance. And so to that effect, this is ARM's highest performance core to date. It is the widest microarchitecture ARM has ever produced, and we do expect it to stack up well in multi-core configurations with anything that will be contemporary in the market when our partners bring it to their respective product launches. And part of that is because the CPU integrates tightly with our on-chip network. So the CMN 700 on-chip network, our next generational of NOC, supports things like high bandwidth memory, DDR5. You can do combinations of different types of extreme performance memory. It also supports PCI Gen 5, C6, and CXL. So there's good connectivity to expansions cards, other sockets. You could do a lot with this platform. Now, the design of a specific implementation of this will be up to our partners. So we see some of the specific design elements coming from announcements from SciPearl and ETRI. So national HPC supercomputing efforts have already picked up the V1 core design and started to put it to good use. As a reference point for some of the Neoverse V1 data I'll show today, I'm going to also show data from the Fujitsu A64FX. The Fujitsu A64FX implements SVE in a dual 512-bit configuration, so each thread has two 512-bit SVE units. It uses a custom Fujitsu microarchitecture, so I'm essentially comparing an ARM core to a Fujitsu core. Even though they both use the same instruction set architecture, the microarchitectures are radically different. And this is in part because the A64FX was co-designed for the specific applications that Riken and the Japanese computing community really care about. It really favors the types of apps that should be running on a system like Fugaku. And so that's reflected in the microarchitecture. And you see that general purpose compute, say commodity HPC workloads, they require a lot of tuning to get performance out of this platform because it is optimized for a very specific design point. Another key difference here is that it implements high bandwidth memory, and this combination of wide vectors with high bandwidth memory has proven time and time again to be a great design point for HPC applications. So you're really looking at a leadership class HPC system here compared to the Neoverse V1, which, while a performance first design, could be used in a wide range of applications, not necessarily only HPC, but really any application where single-threaded performance is a deciding factor. So let's stack these two systems up side by side and take a good look at them. So the Neoverse V1, the first thing and the first obvious difference between the two platforms is that the A64FX actually exists. Neoverse V1 is being done in simulation here. It's not in silicon. This is not a product you can go buy off of the Amazon website. It's a design that somebody's going to have to go implement, and in fact people are implementing. We expect to see implementations of this in a matter of months in 2022. There's generational differences between the platforms. The Neoverse V1 implements the ARM v8.4 instruction set architecture with extensions all the way up to 8.6. The A64FX implements 8.2 with some later extensions. Process differences, they can both be in 7 nanometer, but the V1 can also go to 5 nanometers. Frequency, there's a couple of parameters here that are configurable. What that means is that when ARM designed this CPU, we validate it for certain configurable parameters. Things like core frequency can be selected from a range of options, and ARM knows how the chip will perform for those options. In this simulation, I'm simulating a 3 gigahertz configuration. However, in the wild, you might see different configurations. Vector bandwidth, if we compare the total capability of the platforms, V1 has 2 256-bit SVE units or 4 Neon 128-bit units. This means that whether in SVE or in Neon, the vector bandwidth, the total throughput of compute capacity and SIMD is the same. The A64FX implements 2 512-bit SVE units, so twice the peak performance of the V1 in terms of just sheer vector bandwidth, but it also only implements 2 Neon instructions, 2 Neon units per thread. So the Neon bandwidth is much less than the SVE bandwidth on this platform. Cache line sizes are different. The V1 implements a 64-byte cache line. The A64FX is 256 bytes. However, the amount of L1 cache per core is the same. V1 can have much larger L2 and L3 caches than the A64FX. In this simulation, I'm simulating a 1 megabyte L2 cache per core versus the A64FX's 0.66 megabytes per core. Also, I have a 32 megabyte L3 cache. The A64FX has no L3 cache. Cores per socket, this is one of the key design points for our partners. In this simulation, there are 4 available in the sim, but I'm only using 1. I'll explain why in a moment. A64FX only, of course, has 48 cores, but I'm only showing performance from a single core. To sum it up, the V1 is a newer core with higher frequency. It has half the vector bandwidth of the A64FX, but it does have the same amount of L1 data cache and has more L2 data cache than the A64FX. Because it's configurable, you'll see a wide variety of potential products containing a V1, and I don't promise that any of those are going to match the simulator I'm showing here. This is just as if I was developing my own V1 based platform and I happen to choose these design points. I will say that most of the practical V1 configs do have a lower overall theoretical double precision floating point peak than the A64FX. Given the range of parameters we have here and the TDPs and everything else that you might want to consider, you certainly could match or even beat the A64FX given a certain design point, but most of the practical configurations are lower in terms of overall floating point performance. So how do we project performance of applications on this platform? Well, one thing we consider is the performance of representative microkernels in simulation. And I'll be showing you some numbers from ARM's cycle accurate simulator, the event-based simulator, or EBM. This is a highly accurate core simulator. It's supposed to be within about 5% of a silicon implementation of the core. And because it's done in software, we have a distinct advantage where we can define many more performance counters than would normally be available in a real-world system. We have about 3,200 performance counters here, which means we can get very detailed architectural performance information about the core itself, the L1 cache, the L2 cache, and many of the features built around those structures. The simulator gets a little bit ideal when it comes to L3, and once you're off chip, it's solidly beyond the scope of this simulator. You can go up to 4 cores in the EBM, but usually you're going to use just one. And this is just a limitation of the EBM's ability to simulate things like syscalls and support operating system routines. It's just kind of hard to get a code to run on 4 cores in EBM, although it can be done, and we do it if the data that we'll get back merits the effort. Unfortunately, the simulator is proprietary and not available outside of ARM. In fact, the number of people inside ARM who have access to this thing is fairly low, and that's just because of the extreme accuracy involved. This piece of software is what we use to understand the viability of key design decisions and products built on our core designs. So it really can influence the ARM business model. And essentially that's what I'm showing you here, is that I'm trying to answer some of those questions and bring them back to the community. But I'll freely admit that none of this is reproducible. Now, if you're going to run code on this simulator, you have to deal with the limitations of the simulator. So in a nutshell, the code has to be short and simple. You're looking at an enormous amount of slowdown. So it's usually 1500x to 2000x wall clock slowdown, or a good rule of thumb is if I run 1 second in silicon, it's 30 minutes in simulation. Most of the kernels I'm showing here run for about 4 to 6 seconds. So we're looking at quite at least a day as a runtime to get through all of this if I push them into a queue. Lots of things you have to avoid. I can't use threads. I should avoid dynamic memory allocation, although I will say that I did use dynamic memory allocation in these simulations. It's just you have to be very careful how you use it, and generally avoid anything involving syscalls, which means no threading, static binaries. Keep it as minimal as possible to guarantee the best result. Okay, so that's the tool I'm using. Obviously on the A64FX, I'm just going to run, but in EBM, I'm going to use this EBM tool to simulate the V1 and project the performance of Bliss kernels. How do we compile Bliss? So on the A64FX, I'm using the GCC 11.1 compiler, and I just make a build directory and then configure. I disable the system, disable threading, and disable shared, because that's the same thing I'm doing on the EBM simulation side. I also enable CBLAST just because I have some configs I wanted to play around with there. And I'm using the A64FX configuration. This, I understand, takes advantage of sector cache and provides SVE-based tuned kernels that use a minimum bit width of 256 bits. And then you just compile and run. That's the whole process for A64FX. On the simulator side, I'm using top of tree GCC, so the most recent, latest, greatest, up-to-date GCC I can possibly get. In fact, it's usually even ahead a little bit of what's been pushed into main, because this is the same one our compiler team uses. So this is really bleeding edge compiler where we can rapidly feed back to our compiler teams, try new options, see how those options affect performance in a matter of hours or days. Similar approach, but I'm moving the architecture spec away from the CFlags and into CFlags preset so I can control them very specifically from the command line. So I'm taking out the ARM v8-A plus SVE spec from the ARM SVE config and the ThunderX2 T99 spec from the ThunderX2 spec, which I'm using to measure Neon performance. Because we have to avoid threads, syscalls, all the rest of it, I use this disable system, disable threading, disabled shared flags when configuring Bliss. And I gotta say, this is actually really a pleasant surprise. You can tell that Bliss has been used in simulator before, and the Bliss team have thought about what it's going to take to run these kernels in a extremely minimal environment like EBM. So it was a really pleasant surprise to find that this stuff just kind of builds and works in as constrained an environment as a core simulator. I'm providing an architecture spec of V8.4 with SIMD, so that turns on Neon, SVE, that turns on SVE, and then some additional flags, which actually are redundant in this case, but I put them in there to be more specific. And we're not using any tune flag here. This is mostly just up to the architecture spec. And then we choose either ARM SVE if I want to do an SVE test, or ThunderX2 if I want to do a Neon test. So here's a first look at some of the results. These are the BLIS L2 results. Now, because I can only run on a single core, and I have to keep my problem sizes relatively small, we are looking at some actually very small problem sizes. Our vector length here is only 2K. So take that for what it's worth. These performance comparisons may change if the problem size was larger, and I'm looking forward to silicon access to a V1 core so I can go and test some of these. But at first glance, it looks really good. We can see that the V1 in simulation is both faster and is getting a higher fraction of the theoretical peak than the A64FX does for the same problem sizes. There's a lot of good reasons for this. First, with these small vectors, we're completely inside cache. We're doing a lot of very short-lived operations, and so having a very wide design with relatively short pipes compared to the A64FX allows us to keep more operations in flight. The A64FX is a very narrow design with long pipes, and you really have to almost think of it as an in-order design because of the cost penalty of losing one of those pipes or putting a bubble in them. The V1 can handle complex code a little bit better here, and we're starting to see that in some of these L2 operations. BLIS L3 tells a more interesting story, I think. So here again, we're limited to fairly small sizes. This is a square matrix of 1024 to a side. And if we look at the speed up, we see that predictably the V1 does not outperform the A64FX. And this is, I want to emphasize, this is the specific configuration of the V1 that I've chosen, the 3 gigahertz with the 1 meg L2 cache and a single core. I'm not allowed to talk about the TDPs, but I'm telling you that you can match the A64FX with performance using a V1 based design. And unsurprisingly, we have half the overall vector bandwidth, so our performance is less than the A64FX, but it is greater than 50%. I think this reflects the generational advancements and the microarchitectural advancements that you find in the V1 compared to the A64FX. Not necessarily saying this core is better or worse, simply that it's performing very well using this SVE code. And Probably the most important takeaway here is that the SVE code was written and tested on the A64FX on SVE units that are 512 bits wide. This code is running out of the box without modification of any kind on SVE units that are 256 bits, and it's performing very well. You especially see this in the efficiency numbers. Now, everyone's probably going to be quick to point out that you can definitely get better than 75% efficiency with DGEMM SVE on the A64FX. Totally agree. I think with these small problem sizes, we're seeing some loss of efficiency on the A64FX, and a larger problem size would tell a different story. I'm constrained to this problem size by the limitations of the simulator. So again, take it for what it's worth. This is not a statement about Bliss or about the A64FX. This is a statement about the state of this particular problem size running on designs like the V1. And the ability for the code that was developed on the A64FX to port forward to the V1. It is very encouraging, however, that we're seeing good performance and great efficiency without any code modification. This speaks very well to the idea that SVE code can move forward through architectures even as the vector bit width in the hardware implementation of the SVE unit changes. If we look at the DGEMM performance over a range of matrix sizes, we see that the V1 surpasses the A64FX for these sizes at about 256 bits. I think this is no surprise given the way that the kernels are implemented. It just kind of makes sense. It lines up with the V1 architecture very nicely, very quickly. Speed up normalized to A64FX, we see that the V1 is rapidly approaching about 80% of the A64FX performance overall, whereas the efficiency is closer to 85% of the total available theoretical peak. So showing really good performance, again, vanilla code, not modified, just running the same kernels on the future architecture. Now, one key advantage of running these kernels in simulation is the just overwhelming volume of performance data we can get back. I'm not allowed to show absolute numbers, so the vast majority of these performance points I'm not allowed to discuss, but I can show some relative performance numbers like a couple of cycle breakdowns and things like this. And what we see is that the V1 core is doing a really good job of keeping the SVE units busy, spending most of its time in computation. There is about 30% of the cycles are stalled on the back end, but overall the core is doing really well. This also indicates that we could probably do a little better. You know, these numbers are looking really great, but I imagine that with some tuning we can get even better performance on the V1. So we're not only seeing SVE code run well out of the box on the future architecture, but it's a great starting point for further optimization and enhancement of that code to get more performance out of the platform. So in summary, you know, based on these small performance data points and the little bit of projection we've been able to do based on these really small kernels, it looks like Bliss will perform very well on the Neoverse V1. So any code that uses Bliss should do well, should be able to just run and get pretty close to as much of the theoretical peak of the platform as you would expect, without a lot of tuning and hand-holding and drilling into the code. So that's really encouraging. It looks like the Bliss SVE kernels do in fact just port forward to the Neoverse V1. We also see that the performance on the V1 is more efficient than the A64FX for these small problem sizes. As the problem sizes grow, you know, we might see that curve change. But the challenge here is that for larger problem sizes, you really want to be able to simulate a whole system on a chip, a whole SoC. Now, ARM provides CPU core IP. We provide the ARM chip on-chip network. But when you get to the L3 cache and you start to go off and connect to accelerators and go beyond, basically once you're beyond the L2, you've left the domain of ARM IP, and that is really the realm of ARM's partner. So if we were to study these larger problem sizes, we would have to fix some of those design parameters based on the designs of ARM's partners. And that means that I can do it. I can certainly use SOC modeling tools and try to approach that problem, but I'm using data from ARM partners to sort of simulate their designs. Once I'm doing that, really the best quality data is going to come from the partner. I've kind of left my domain of expertise. So I would look to an ARM partner implementing the V1 core for a more detailed study of these kernels at scale. But given that the V1 will be in silicon available to a lot of people very soon, I don't really see the point in spending the effort. Just wait a little while. You'll have it in your hands and you can do the tests for yourself. Also very encouraging to see the current state of the LLVM and GNU compilers for the Bliss kernels that do rely on the compiler for performance. No performance or correctness issues that I could see. Everything looked great. This suggests strongly that a lot of codes using Bliss will do well, and codes that use their own implementations of numerical algorithms will do just fine as well. So I think the V1 is looking pretty good here. So that's my talk. Thank you very much for listening, and I'll be happy to discuss this with you at Bliss Retreat. I'll see you there. Thanks. Bye.